So we're going to do a couple of word problems associated with section 4. So let's let's look at problem 61. So let's go ahead and read it. Jack Adrian, a friend of one of the authors of this text, has a beautiful 14th floor condo with a stunning view in downtown Chicago. The floor is 150 feet above the ground. Knowing that this author is a mathematics teacher, Jack emailed the author and told him that he recalled once having studied a formula for calculating the distance to the horizon, but he could not remember it. He wanted to know how far he could see from his condo. The author responded, to find the distance to the horizon in miles, take the square root of the height of your view and multiply that result by 1.224. That will give you the number of miles to the horizon. Assuming Jack's eyes are 6 feet above his floor, the total height from the ground is 150 plus 6, or 156 feet. To the nearest tenth of a mile, how far can he see to the horizon? Okay, so all we're really doing in this is we're just taking that equation and writing it out and then plugging in the number. So it says to find the distance to the horizon in miles, take the square root. So we'll say distance is equal to the square root of the height of your view, which in this case is 156, and multiply that result by 1.224. So let's just use our calculator to make sure we know how to do square roots. So we have the square root of 156, which I'll go ahead and calculate, is 12.49 times 1.224. So 12.49 times 1.224. And so that's 15.3, and I guess the answer says that will give you the number of miles. Okay. Let's do 62. The formula I equals the square root of 2p over L relates the coefficient of self-induction in henries, the energy P stored in an electronic circuit in joules, and the current I in amps. For the value of I, find the value of I if P equals 120, L equals 80. So here's our equation. So all I have to do is just plug the numbers into the equation. Again, it's really just testing our ability to do square roots. So P is equal to 120. L is equal to 80. And so what do we get? Well, let's go ahead and calculate the term in the parentheses, which is if you multiply 2 by 120 divided by 80, you get 3. And so if you take the square root of 3, you get 1.73, and the book rounds it off, and the units are amps, because it says the formula I blah blah blah. It should say that the current is in amps, so that's the result. Okay, 67. It says the length of the diagonal of a box is given by this formula. So the distance of the diagonal is L squared plus W squared plus H squared. This should look kind of familiar. It's really the Pythagorean theorem, but applied to 3 dimensions instead of 2 dimensions. So Pythagorean theorem would just be in 2 dimensions, and one of these would go to 0, and you just have the square root of the sum of 2 squares. So in this case, we're asked to calculate the diagonal given the following information. And as long as the units are all consistent, which they are, they're all feet, we have, let's see, the length of the diagonal, and it doesn't really matter what we call length, but their height. We're going to get the same numbers. So you take 4 squared plus 3 squared plus 2 squared. So it's got to be greater than 4 because we have this additional stuff. How much more? I don't know. We'll see what happens. So let me go ahead and multiply these out. 4 squared is 4 times 4, which is 16. 3 squared is 3 times 3, which is 9. 2 squared, which is 4, which is 2 times 2. So we add those all together. And 16 plus 9 is 25, plus 4 is 29. And so the square root of 29 is equal to 5.39. And the book says 5.4. And the units were feet. So the original units were feet, and they were all feet, so the final answer is also in feet. And let's do one more. It's number 70. And it says, in the static sound, one version of the law of tensions is F1 is equal to F2 times the square root of capital F1 over capital F2. And basically what this is really talking about, what we're talking about is like the tension in a string for a violin or a guitar. And so if you say if you know frequency F2 and you know the tension for that frequency, if you want to calculate what the frequency is at a new tension, so if you increase the tension, you're going to make the string tighter, and that's going to give you a higher frequency or higher pitch. And likewise, if you have a lower tension, you're going to have a lower, this is going to be lower, and the square root is going to be lower, and so you get a lower frequency. So in this particular case, we're asked to calculate an F1 given these quantities. So the original frequency is 260 hertz. We multiply that by the square root of F1, which is 300, and F2, which is 60. So we start out at 260 hertz, we have 60. So if we increase the tension, we should increase the frequency, which is going to happen. And so we get 260 hertz times the square root of 5. 300 divided by 60 is 5, because 30 divided by 6 is 5. So we take 260 times the square root of 5, which is going to be 581. Okay, I think that's enough of the word problems.